let's take a look at your homework here. Now, a little change of plans. We're going to quiz on Monday. Okay. Well, there were so many people who got on Tuesday, so blame them. Actually, it works just fine. It was, but what we're going to do? So tomorrow, because I'm not going to be here. So tomorrow there will be, have a couple of different things to work on. One of the things we were going to do was kind of long term, which are packets. So I'm going to go ahead and give these to you now. Well, I'll talk about it more specifically. So this is, like I said, this is more, the small one is kind of related to what we're doing now. So we'll kind of have several different kind of things going along here. And then this is the next of our big major packets that we'll kind of work steadily on as we go through the rest of this year. So I'm just going to give it to you. What's that? What on this? No. Okay, so the sample 3 packet, and then this tabular data packet. So this is just like 6, the tabular data packet is kind of like 6 free response questions that are kind of like free response questions, but they deal with tables of data. And so we looked at one from 2016 the other day, and so this is kind of practicing that kind of thing. So there'll be a little bit of that on this quiz. We've been talking about Riemann sums a little bit, but so these aren't really for Monday. These don't have to be done. None of these things are done for Monday, but they're things you could be working on tomorrow. But I've got a video from last year, and I went through and I watched it. It's right on line with what I would be doing tomorrow if I was here. I mean, I should do that all the time. I should just come in each day and assign you to watch the video from last year, and I'll put my feet up, relax. But well, I should do that. But anyway, it's pretty. I mean, it would be just what we would be doing. It'll review. It'll go over a few of the homework questions, and you'll probably have. I will be here early Monday morning. If there's something on the video that you don't get answered, if there's some homework question I give you today that you're still wondering about and want to ask, I'll be here early, Monday morning. But otherwise, so you can watch that on your own time, or you can use class time tomorrow to watch it. Bring headphones, and watch the video. I think I put down. Well, let's see. I've got it on our website. I think it's 56 minutes total. So it wouldn't take all of class time, but if you go down here to the homework section, Friday, March 2nd, it's already up there. Watch video from last year for review. Only watch up to the 56-minute mark. I accidentally left it running. Okay, but I don't think any grades show up or anybody's email or anything like that. So you can stop it at the 56-minute mark unless you want to listen to the class. And then the quiz is Monday. So this is the link. Okay, so you can bring headphones tomorrow and you can watch that. If you'd rather say, hey, I'll do that this weekend sometime, whatever, and want to work on the packets during class time, you can do that. So Mr. Templey's a sub. I left him a note that you would be working on one or two of those things or both. Right? Watching the video or looking at the packets or working through those packets a little bit. Okay? Like I said, sample 3 is one that we'll just kind of work steadily on. We'll probably have a little bit of work time on it on Tuesday again. We'll probably spend part of Tuesday because I know some people will be gone. We will be moving on a little bit on Tuesday as well, but we'll probably be working in those packets, talking about those a little bit on Tuesday. I'll record that for people that are gone. Okay, so it just won't be quite as much of a hassle for you guys to get that made up. Okay, so with that said, let's talk. Any questions on? I want to look at 23. okay? But is there any other ones there that you want to check or take a look at or anything? 11, okay. Any others? Okay. So one of the things for sure that will be on the quiz is you've got this in an integral, and you're going to want to convert that into a sigma. Now, there's when we talk about converting an integral into a sigma, remember what the sigma is just adding up. The sigma is just adding up a certain number of terms. And so if what we're adding, so the true integral, and this is what I was emphasizing the other day, if there's an equal sign in between here, then you have to be adding up an infinite number of rectangles. So you might be doing a sigma that represents an infinite number of rectangles. All that means is you do n subdivisions, and then you stick an n goes to infinity out front. Or, more likely, most of the time, the problem is an approximate, and it's adding up like 20 rectangles, or 15 rectangles, or 4 rectangles, or 50 rectangles, or whatever. Okay, then the sigma is just an approximation of the area of the unit. Okay, so that's kind of what we're doing here is this kind of thing. This integral could be approximated by or represented by this sigma. Okay, on 11, the one with the k goes 0 to 9, that one. James, is that the one we're looking at? It says k plus 1 squared. Okay, now there might be a couple like this on the quiz, right? Where I just basic sigma problems, I just say find the sum. Now, and Harish just asked this, on the quiz, there's going to be, the summation formulas up at the top of the page, right? So you've got a couple of options on this one. One option would be to just plug in a 0 and you get 1 squared, and plug in a 1 and you get 2 squared, and plug in a 2 and you get 3 squared. And so this is going to go all the way up to 10 squared, right? And you get out, let's see, I'm going to let you have calculators on this one, by the way. Okay, and we are going to use calculators, okay? So you can get your calculator, you can add those up, okay? Now, what you can't do is just type this in, because there is a sigma on your calculator, right? I mean, I don't know if you guys have looked at that yet, but where the derivative in the integral is, you can't just type this in your calculator and get the answer, right? Now, with that said, when I say that, I'm saying I want you to write out the sum, right? And then I'll have you value it. Now, how am I going to know if you typed it into your calculator and added it up, or if you just typed in the sigma? I won't. So from that, so I guess when I say you can't just type it in, I'm saying you have to write out the sum, and then you add it, right? Now, there will also be some, and this could be one of them, that I'll say use the summation formulas to find the sum, okay? So then I'm looking at your work where you would maybe take this. Now, I didn't say that on this problem, so I'm assuming you didn't do that, okay? But now you can take this and you can say, okay, this is k squared plus 2k plus 1, okay? And we could write that as sigma k squared. Let's just do that for a quick review here. And sigma 1. Okay, so this is going 0 to 9. Oh, wait a minute. We couldn't do that. And I'm not going to trick you on this. Why wouldn't this work for the summation formula? The summation formulas only work when the sigma goes 1 to n. 1 to n. Okay, so so let's pretend just for a minute that this said 1 to 10. Okay, if it said 1 to 10, then that's when we do our n and our n plus 1 and our 2n plus 1, right? And so if this said 1 to 10, we'd have 10 times 11 times 21 all over 6, and and then go from there. Okay, so if it said use the summation formulas, but I won't try to trick you on that. Okay, so now that I said that, and I said there's a couple different ways to do this. Another way to do this one actually would be to rewrite this. I mean, look, now that I've expanded it out, what's another way to rewrite this sum? K goes 1 to 10 and k squared. Now we can do the summation formula, right? 1 squared plus 2 squared plus 3 squared. This is exactly the same as this. Okay? And so we've got that. So now we can do that summation formula. Now we could do 10 times 11 times 21 divided by 6, and that would be the sum on this one, right? That would be the sum. So if I gave you this and said use the summation formula, I'd want to see that, and then okay. But if we get into a table of data, or we get into Riemann sums, I want you to have 4 or 6 or 8 rectangles. Something. I want to have you spend a ton of time doing it by hand. So that's the only thing you're going to really need your calculator for, maybe, is to add up some stuff.
So are you going to tell us when you want us to write it out?
Yeah. So if I was giving you a problem like this one where it says evaluate the sum, I would say write out the sum and then evaluate. Okay. If I wanted you to do summation formulas, I would say use the summation formulas at the top of the page to find the sum. So I'm going to be really clear on those directions. Okay. All right. So let's talk about number 23 here. 23, let's just pick one of them out here. Let's, the first one said to do 10. I just wanted to do another midpoint one with you. Okay, so we're supposed to write this as a sigma. So this obviously, hopefully obviously, is a square root graph. It's 0 to 5. We're talking about this area right here, right? But we want to do some midpoint rectangles, right? So we're going to go from 0 to 5. And we're going to do 10 subdivisions. So the first thing we do is the width, which would be 1/2. So we're going to be at 1/2. We're going to be at 2 halves. We're going to be at 3 halves. And we're going to go all the way to 10 halves, right? So our very first midpoint is going to be where? Where's our very first midpoint going to be? Right there, right? So that's all of a sudden when we say, okay, this is like 0 4ths, and this is like 2 4ths. That's a pretty easy one to find. The other day it was a little harder. We had 3/10, and so we're trying to find that midpoint. We had 23/10. We're trying to find that midpoint. So we had to get, we had to bump up the denominator on those so we could get a midpoint. Now, between 0 and 1/2, finding the midpoint is pretty easy, but it would be kind of like doing this, right? 0 4ths, 2 4ths. Oh, okay, 1/4. So the first one's going to be f of 1/4 times. Well, now I had said this. This is going to come into play today. I had said this the other day. Is that when you notice this, when you notice that the denominator's double on one of these, the width compared to where you're at, that usually is a signal that you're doing a midpoint. Okay, because that's what happens when you do half. You double the bottom number. But sometimes they will, like I said, it's sometimes nice to write these not reduced because then you can see patterns better. So sometimes you will see them do something like this, right? Well, they'll write that width as 2 4ths instead of 1/2. Well, now all of a sudden your denominators look the same, and then you might get fooled into thinking that this isn't a midpoint situation, right? So you got to be careful of that. When you see that kind of scenario, understand that this is 1/4 is half of the width, so this is a midpoint one. So just like I said, this is kind of a giveaway when you see that it's a midpoint, but sometimes it could be rewritten in such a way that it didn't look like that and still be a midpoint, so be careful. Okay, what's the next one? It'll be 3/4. Now, you got two ways of doing this. You can come back over here to your x-axis and you can say here's 2 4ths, here's 4 4ths, so halfway is 3 4ths. Or you can say, all right, from here to the next one over is one width, right? You go from every point, you go a width over. So from 1/4, we got to go one width over. So we got to go 1/4 plus one width, which is a half. So 1/4 plus a half, 1/4 plus 2 4ths is going to be 3 4ths. And then it's going to be 5 4ths, and then it's going to, 5 4ths. And this would be 7 4ths, and so forth. And you can get the last one, but I usually don't care about the last one, especially on midpoints. Okay, so now we write our sigma. I equals, we usually do start at 1 here. Okay, what is this going to be? 1 to what? 1 to 10. Don't forget that these numbers here have very little to do with these numbers here. The only thing these numbers have to do with these numbers is in finding the width. The 5 minus 0 divided by the 10 is what the width is. So they're a little bit connected, but really not. The mistake people always want to make is go 1 to 5 here, 0 to 5 or something. They want those numbers to be the same as those numbers, and that's not true at all. Okay, this is how many subdivisions you have right here. Okay, so this is going to be F, parentheses, parentheses, a 4 on the bottom. Leave that alone. We got a 1/2. Every term is going to have that. Now, how do we generate a 1, then a 3, then a 5, then a 7? Well, it goes by 2, so that makes you think of what? 2i. So what are we going to have up here? 2i minus 1, probably, right? So it goes by 2's. That's going to make you think of 2i, but 2i would give you 2 at the first one. We want 1, so we're going to have to subtract 1. So 2i minus 1. So you just make an adjustment, and you got it, okay? And then the last thing to do is to plug it into your function, take it out of sigma notation. So we go I equals 1 to 10, and so we're going to have square root of 2i minus 1 over 4 times 1/2. Sometimes you'll see in the answer book, or maybe you'll see, because today what we're going to do is go backwards. We're going to have our sigma, and we're going to go back and figure out what the integral is. It's actually easier than doing this way, less work. You got to kind of be able to see it. Sometimes that's a little trickier, but once you get the hang of it, it's really pretty easy. This way, you just got to write it out because you got to see the pattern to get it. Now, so the 1/2 sometimes thrown out here in front. Sometimes you could split that up, like you could simplify that. You could put square root at the top, square root at the bottom. You know, and square root of 4 is just 2. I mean, I don't want you to do any of that. I'm fine with you just leaving that way. So there will be problems on there where here's an integral. Write a sigma that represents M10. Write a sigma that represents R4. Right, whatever. Okay, and then I might say to evaluate it. Now, probably not with an M10, but if it was an M4, I might say go ahead and evaluate, right? And write it out. You know, and again, I'd want it if it was just 4 of them or so, we'd write it out. Here we wrote out a couple just to get the pattern. Okay. And then, so the other ones would be pretty simple. Okay, so it's definitely an emphasis, definitely something you'll have to do on the quiz. All right, anything else? That was about it on that homework. Okay, all right, so let's revisit something we talked about the other day. This is back on page 355. Again, these tables of data. I want to talk about this. Now, I think we did the trapezoid one in class yesterday, didn't we? We did 27. I think we did number 25. And we did number 27. I don't think we did number 26. So let's look at that one together here. So here's a table. So it says the integral from 1 to 5, and we want to write out and then find R2. Okay. Well, matter of fact, just do it real quick. Find out. All right, just find R2, right? Find it. Basically, the directions would be, here's f of x, this is function f of x. Find a Riemann sum approximation, a right Riemann sum approximation with 2 subintervals for the integral 1 to 5 f of x dx. That would be the question. And I'll go get more coffee. right, what do we got? What's the answer?
1.4.
Yes. Well, yeah, because I just walked in, I said, oh, okay, that'd be 0.72. So I had 0.72 in my mind. But what was I forgetting when I did 0.72? The width is 2, right? The width is 2. So again, it would be, at this point, I would encourage you to, and I would probably say write out the sum and then evaluate it, right? And so I think it would be good to say, okay, from 1 to 5, and again, your x-axis is good to draw, and we're going to do two subdivisions, so that's going to be, 5 minus 1 divided by 2, right? So we're going to get a width of 2. So we're going 1 to 3, but your first right is there, this right. So you're looking at that number, but the width is 2. So it's going to be f of 3. So your first right is going to be f of 3 times 2. Your next right is going to be f of 5 times 2. So again, I think you can really keep this consistent with what we've been doing. And that's what I've been trying to do through sheer repetition and drill here to hammer this into you. And so I think maybe, hopefully, we're getting it pretty good. So, do this, find your width, do this, da-da. But on a pretty, at some point, hopefully, something like this would become pretty simple, where you would just look at it and say, oh, okay, 1 to 3, that'll be there, and then there, that'll be 2 of them, here's the right endpoint, and at that. Then even I forgot about more point by the width. Okay, so that's why it's not a bad idea to write it down. And that works whether it's a graph or an equation or a table of data. Okay? All right. So on that packet, let me just say this now. On that thin packet, the one with the tabular data, if I was going to work some problems tomorrow or this weekend that might be related to the quiz, I think on each one of those 6 pages, there's a problem, at least one of the parts that talks about doing a Riemann approximation. It'll say you do a right Riemann approximation with 3 subintervals. Do a trapezoid approximation with 4 subintervals. Those would be the ones I would pick out of there. The rest of the problems are probably more just related to long-term stuff we want to be able to do, not necessarily the quiz. Okay, so pick out the part of each one of those problems that does something with a Riemann, and then that would, or a trapezoid, that'd be a good problem to do. Okay, so it'd be very similar to this. All right, well, let's get going with what we're going to do today. Okay, so let's put that in your notes, and we'll talk about this problem. So this problem is, so the directions on this problem, if you want to write it out, the directions on this problem would be write the integral that is approximated by this Riemann sum. Write the integral that is approximated by this Riemann sum in sigma notation. So, right? So, what would be the first thing that would stand out to you on this one? They're left rectangles because of the 0 to 9. Now, is that important? Not really, but so let's kind of go through kind of the long way of how you can think your way through this, and then I think you're going to start to see, you're going to start to see how you can get the answer to this in pretty short order without really showing much of anything. Okay, so we got to kind of think backwards from what we did here, right? So what did we do here? So on this one, we would be looking at this, and I would have saw the 4 and the 1/2, and I would have saw, this might have been a midpoint. But what I would do first is I would start plugging in i's of 1 and see what I get. I mean, I kind of want to go backwards. So if I plug in a 1, I'm going to get square root of 1/4, right? Well, that's Here's my function. So square root of 1/4 means the first thing that got plugged into the function was a 1/4. So now I'm thinking of a number line, and I'm thinking, okay, the first thing that got plugged in is 1/4, because kind of thinking my way backwards. Now, I right away also noticed this, probably that's the first thing I noticed, is that's my width, right? I know this part's my function, because the square root obviously is a function. So what's my function on this one, do you suppose? Don't you suppose x squared is your function on this one? What do you suppose your function is on this one? Sine. What do you suppose your function is on this one? You see what I mean? So right away you can look at it and you can say, well, that's my function. I bet that's my width. I bet that's my width. I bet that's my width, right? So you can just look at it and kind of tell what the different parts are. So I have a feeling that's my width. So here I know my width is 1/2. So right away, by just plugging a 1 in for I got square root of 1/4. And my width is 1/2. And I already had an idea because of the 2 and the 4 that this was a midpoint situation. So right away, that tells me, okay, my width is 1/2. The first thing I plug in is 1/4, right, which is a midpoint. So that tells me this integral must have started where? At 0, right? If my width is 1/2, the first thing I plug in is 1/4, then that means that had to be between 0 and 1/2. Now, if the first thing I would have plugged in is 1 1/4, think about this now. If the width is 1/2, and the first thing I plugged in is 1 1/4, what must this have been right over here? What must have my far left edge have been? Would have had to been 1, right? I mean, if my width is, here's my far left edge, if the first thing I plug in is 1 1/4, and I know the width is 1/2, then that means from here to here has to be 1/2. This is 1 1/4. That tells me that would have had to been 1, and this would have been 1 1/2. So that tells me my integral must have started at 1, right? But in this case, it tells me it started at 0. You see what I'm saying? So when I got this, what I'm trying to figure out is what did my integral look like? So I need to figure out where it started. I need to figure out where it ended. I need to figure out what the function is. And then what's going to happen to this 1/2 when I write my integral? It's going to disappear, right? Because in the integral, the width is like the dx. So the 1/2 is just going to disappear, and it becomes the dx. The square root was my function, so the function ends up being square root of x. And so what I do is I start by plugging a 1 in for I and think about the width and so forth to tell me where did this start. Now, if I figure out now that it started at 0, then where is the ending? How do I get the ending, do you suppose? Well, that's also over here. What do I do? Well, to get the start, I plugged in a 1. So let's plug in a 10. So let's plug in a 10, and we get 20 minus 1, which is 19/4. Well, what is that? 19/4. Well, that's 4 3/4. Oh, 4 3/4 would be the midpoint. That would be all the way over here next to what? 5. Well, it's half a width away, right? The last midpoint is half a width away from the far right edge. And so that's going to be 5. Now, the biggest mistake people make on these problems is they put in the integral and they plug a 1 in here and they get 1/4. And then they plug a 10 in here and they get 4 3/4. And they think the integral is going to go 1/4 to 4 3/4. Okay? Couple things. Is that possible? Could you have an integral that goes from 1/4 to 4 3/4? Absolutely you could. I'm not going to do that here. On these problems, your integrals are going to go to nice whole numbers. Okay? So you're not going to get, and no matter how many times I say that, somebody's going to do it on the quiz. Okay? But your integrals are going to go to nice whole numbers. Right? So the reason I'm getting 1/4 when I plug in a 1 and I'm getting 4 3/4 when I plug in a 10 is because that's my sampling point of my rectangles, right? And so 1/4 is right half a width away from 0, and 4 3/4 is half a width away from 5, and those are my endpoints, 0 and 5. Okay, so that's what we end up with. Now, the other mistake people make is when they write their integral, they'll put square root of, and then they'll do something like 2x minus 1 over 4, something like that. No. Okay, think about all the problems we've done like this. All the ones where we started with an integral and ended up with the sigma. the integrals have always looked nice and neat like this, haven't they? Square root of x, ln x, x. Could they be more complicated? Sure, they could be. Think about your gateway test, right? But they could be more complicated, but they're not, right? So we're gonna start with just nice, simple functions, nice, neat integrals. Those make messy sigmas. Integral. What would be the opposite of messy? Neat, neat, neat. Clean, clean and neat. Integrals, clean and neat. Sigma, messy. Integral, clean and neat. Sigma, messy. Okay? So when we go backward, so it's perfectly reasonable when we start with a nice, clean, neat integral that the sigma we end up with is kind of messy. Well, now going this way, it's reasonable to assume that this is going to start out looking real messy. Our final answer is going to be clean and neat. Okay? So, let's go through this. So, think about my number line. What do you notice here? We already thought it might be lefts. I would probably see that right away. What's that tell you? What's this right here tell you? That's the width. So I'm going to have a width of 2/10. So I don't really know where I'm starting yet, but I know I'm going to have a width of 2/10. So the first one over, that's going to be a gap of 2/10, right? I think my integral is, we're thinking x squared is going to be the function, not 2x squared, not 2x over 10 squared, just x squared. Because remember, it's like German shorthand, right? We take the German shorthand and we plug it in for the x. We take the x plus h and we plug it in for the x, right? The 2I over 10 is what got plugged in for the x. So that part that's changing where you see the I, that's where the x was, right? Because that's the part that changes each time. So the messy part inside, that's where the x goes. So this is going to be x squared. And of course the 2/10 is going to disappear and turn into what? Dx, right? So this is pretty easy right now. So all we got to do is figure out where it started. Now again, people put 0 to 9, and that's wrong, right? This is where we have a little bit of work to do. So we're going to put a 0 in for I. That'll help us get started. And we'll put a 9 in for I, and that'll help us get our ending. And that's it. So we put a 0 in, what do we get? Oh, and since we already think, like Matt told us, this is a left, right? Well, what's the first thing you plug in when you do a left rectangle? The far left edge, don't you? You plug in the far left edge. So if you think these are left rectangles, then the first thing you plug in will be your left edge. Unlike this one, where the first thing, when we put a 1 in here, we got 1/4. Well, see, that's why it was good to kind of have a feeling what rectangles are we looking at. So the first thing we plugged in here, when we put a 1 in, we get 2 minus 1, we get 1/4. 1/4 was plugged into the square root function. That's half a width over. Oh, so that's a midpoint. It's half a width over from where? From 0, right? 1/4 is half a width over from 0. 0 must have been our left edge where we started. Okay, so this one must be starting at 0. So this is 0. Then the next thing we plug in when you put in a 1, that'd be 2/10. Makes sense. The last thing when you put in a 9 is 18/10. So when you do a left, you always stop short of the far right edge, right? So that means that's 18/10, which means this must be what? 20/10 or 2. So this integral must be that. Sigma, messy, integral, nice and neat. So this is 10 left rectangles that would approximate that integral right there. Okay? So we're going to want to go that direction too. Now I think once you get the hang of it, this direction is quite a bit easier. Another way you could get the ending point instead of putting in the 10. You got to get the starting point by plugging in this, right? There's just really no way around that. You've got to plug this in to get your starting point. But once you know where you're starting, you could say, how many rectangles are there here? 10. What's your width of each one? Number of rectangles times the width of each rectangle, wouldn't that give you total width? So 10 times 2/10 is 2. So if you know you're starting at 0, then you're going to end at 2. If you were starting at 1, then you would know you'd end at 3. Does that make sense? So that's another way you can do it, is you can have how many rectangles do I have times the width of each one, that'll give me my total width. That's the B minus A, right? And then you could get, I mean, think about it. Our formula was delta X equals B minus A over N. So if we take N times delta X, that's going to give us B minus A, which is our total width. Okay, our total width. So once you have that, then you can do that as well. Okay, now, I will say this, though. Well, that wouldn't happen on this one, so we'll come back. We'll revisit that. Okay, let's look at this one. Okay, so you take a crack at it. You take a crack at this one and see if you can come up with what the integral would be. That this would be representing. Chloe, just going backwards from what we were doing. You know, we were doing the integral, like today's homework was the integral, and writing the sigma of the sums. Now we're just going the other way. Here's the sigma. What was the integral that created that? So it's just kind of going in reverse. Now, remember when we were talking about sigmas and we said there's really an infinite number of sigmas depending where you started, right? I 1 to 10, or it could be 0 to 9, or it could be 2 to 11. We didn't really get into those. We were either 1 to 10 or 0 to 9 with lefts or rights. But you could tweak the formula and change the starting point, and there's an infinite number of answers. And the same thing is true with the integral. There's actually an infinite number of answers you could give for this, right? Now there's one that probably everybody's going to come up with, and maybe a second one, and I want to talk about that on this one. So what is, somebody want to volunteer what they got here? What's a function? Sine x dx from 2 to, okay? That's it. I mean, without doing very much work at all. Okay, now let's talk about how you would go through that. So let's talk about how you would go through that. So, all right, let's do, okay, so this would be the red answer. Oh, so what I would do if in looking at that is I would say, okay, this part in here is the messy part, the part where the x must be. That's the part where the I is. That's the part where the German short hair, right? That's the part when every time I changes, we get a new value. And so as we go along our x-axis to our different widths, right, that's where the x must have been. So this must have been the function sine x. And then the 5/100ths, of course, is our width. And so that's just going to turn into, the dx when we do the integral. Because remember, the integral is how many rectangles? Infinite. This is how many? This is 100. Right? This is 100 rectangles. This is infinite rectangles. So the width goes away. Now is this 100? Are these left, rights, or midpoints? Can we easily tell? I would say they're rights. Because these were lefts because we saw the 0 to 9. So that told us they were lefts. These are either going to be rights or midpoints. And because this has a 5/100 and this has a 5/100 there, that tells me that these are rights. Okay, that bottom number is not double like it was with the midpoint one. And so that tells me every time I increments, we're going to add on another 5/100ths, which is one width, right? We're going to move over one width from there. Okay, now, how do we get the 2? Well, you plug in a 1, right? How do you get your starting point? So we get the sine x from knowing that that's where the x must have been. This is going to be our dx. And then we just need our starting point, so we plug our starting point here. So we put a 1 in, and we get 205 100ths. Well, if you think about your x-axis here, if the first thing you plug in is 205 100ths, right? The first thing that gets plugged in, and when I say plugged in, I mean where the x is, and we've all decided that this is where the x is, right there, right? So if the first thing that's getting plugged in, I know we're plugging a 1 in for I, but the first thing plugged into our function, which is this red circle, the first thing is 205 100ths, and 5 100ths is the width, then what's our left edge have to be? 200 100ths, which is 2. Okay, now how'd you get the 7? Plug in 100. Plug one way is to plug in 100. So to get your ending point, plug in 100. That'd be 200 plus 500 is 700. So, and since these are rights, the last thing you plug in on a right rectangle is the far right edge. So 700 100ths would be 7, and there you go. Or you could say, how many rectangles? There's 100. Each one is 5 100ths wide for a total width of 5, right? So if it starts at 2, total width of 5, it's got to go to 7. Now, did anybody have their integral starting at 0? Here's what you could have done. Let's do that in blue. Another way to think of this in here, and I don't know, it depends what's easier, what you think's easier or harder. Most people think let the whole messy inside be the x. So square root of x, sine x, e to the x, yes. I think that's probably the way to go. Okay? But another way to look at this, because this problem might have been given to you this way. 2 plus 5i over 100, right? Isn't that the same thing right there? Right? Isn't that the same thing as that? Split that fraction apart. Now, sometimes people look at this and like that because basically that tells you your starting point as well. That when you have 2 plus, because think about it, if the width is 5 100ths, every time I changes, you're going to add another 5 100ths. So you're going to start at 2 and you're going to add on 5 100ths, add on 5 100ths, add on 5 100ths. So written this way, that's kind of nice. Kind of tells you your starting point is 2. But again, that would be letting all of the inside be the x. What would be another thing, though, we could let be the x? What if we said this is really the only part that's changing? Right? Isn't that inside there? Isn't that really the only part that's changing? The 2's not. Couldn't that circle be the x? So let's look at that. So let's say we did that, and now our integral is what? Or our function is what? 2 plus x. Right? With me? Okay? Because remember, we said this big red messy part, this is the part that's changing. Every time I changes, that whole red circle is changing. So that's where the x is. Okay? Well, if we split it up this way, we could argue that this is the part that's changing. So we could just put the x there. Okay, now, that changes where we start. Because now when I plug a 1 in for I, what is getting plugged in for the x? Not what's getting plugged into the sine function. What's getting plugged in for the x? Because the x is just this circle part. So when I put a 1 in, I get 5 100ths. And then I put a 2 in, I get 10 100ths. So that's telling me that the very first thing plugged in was 5 100ths. Well, then what must this have been? 0. So now this integral would have started at 0. Now what's the total width? The total width is still 5. Would this be a correct answer? How does this graph compare to that graph? What's sine of 2 plus x compared to sine of x? Isn't that shifted left 2? Isn't 0 to 5 just shifted left 2 from 2 to 7? Don't these have to represent the same piece of area? Has to be the same piece of area. You got the sine graph from 2 to 7, and then you just shift the graph over 2, now it's from 0 to 5. Now you got the graph shifted left 2, it's from 0 to 5. So, either way is fine. I think probably most of you would do the red. right? You would just take all the messy stuff so you would have, even if it was written 2 plus 5i over 100, you would have just taken this and you just said, okay, that is all my x right there. That whole part is my x. So this is going to be sine x. Okay? What you don't want to do is kind of combine these two, right? You don't want to do sine 2 plus x and then start it at 2 and go from 2 to 7, right? So that's why I like to circle it, because I like to circle that messy inside stuff, and I like to think that's my x. That's my x. So if I'm doing the blue, that's my x. So when I put my I in, I just think 5 100s, 10 100s, right? And then that means it must have started at 0. So if you do that, then you can make your integral start at 0 almost every time. Okay? So if you like it and have your integrals always start at 0, then you're going to have something a little messier in here. If you want to keep just a plain old x in there, then your integral may start somewhere different. So you have that option. Okay? One more. Okay? Now this one looks awful because of, oh man, it's just a mess, and it's got that infinity in there. Does that change anything? Other than what? How many rectangles are there? So this is actually the integral. The integral we come up with is actually equal to this. I don't know if I've been putting equal signs in. I probably haven't put anything in. But these two problems were not equal to the integrals we came up with. They're approximations of those integrals. This would be actually equal to the integral we come up with. Okay, go ahead and give that one a try. Remember, the fact that it's messier does not mean it's harder, right? You expect the sigmas to be messy. All right, somebody got something? What's your function? E to the x, dx, from 3 to 6. Anybody try that other business I did with, because you could do that here, right? What could you have on the inside? E to the 3 plus x, and then it would be from 0 to 3. Okay? All right, let's go through that. Okay, again, sigma, messy, the integral is going to be nice and neat, right? So, thought process, probably most of you thinking about the red, right? So all this messy stuff inside of the function is where the x would go. because the x is the inside of the function. So the red, so ignore the black right now, just look at the red. So the red is the x, right? So that's going to be the x. We got it. Of course, we look at that right away. Think that's our width. 3 over n is our width, right? 3 over n is our width. So I come over, so that's going to be my dx. So I think it's going to be e to the x. So what's the first thing I plug in? I plug a 1 in for k. I get 2 minus 1 is 1, times 3 is 3. I get 3 over 2n. Oh, when I see that 2n, what am I thinking? Midpoint. You see 2n, where the width is n. Remember, if the bottom number's doubled, that makes you think midpoint, because that's how you do a midpoint, because here's what we're going to do. So if the first thing I plug in is 3 plus 3 over 2n, that means I added on 3 over 2n, but my width is 3 over n. Well, 3 over n is the same as 6 over 2n, right? Double the top and bottom, take top and bottom times 2, so 3 over n would be the same as 6 over 2n. So half, so that's one width. That's one width while I'm looking up here, I guess, because I don't really know that I'm starting at 3 yet. I have an idea, it's like 3 plus, right? So 3 plus 3 over 2n, that's like half a width from 3. So that tells me I must have started at 3 here, right? So 3 plus 3 over 2n, well, the width is, 3 over n. Well, that's 6 over 2n. So 3 over 2n is half of that, right? That's where you get that midpoint, okay? But you don't have to get that lost in all that. You just have to think 2n, n, okay, that's halfway, that's a midpoint. It's the 3 plus that's the important part there. That's what tells you you're starting at 3, okay? And then you could either plug an n in here, now that gets a little messier, or you could just, this is, a problem like this is why I showed you that other way. You could just say, well, wait a minute, I got 3 over n, I got 3 over n is my width. 3 over n is my width, and how many rectangles are there? N. So I got a total width of 3. But you could plug an n in here. You're going to get 3 times 2n minus 1 over 2n, and then 3 plus that. So that'd be 3 plus, and then this is going to be what? 6n minus 3 over 2n. That'd be 3 plus 6n over 2n minus 3 over 2n. What's 6n over 2n? 3. 3 plus 3 is 6 minus 3 over 2n. Oh, okay. So what's 3 over 2n? That's half a width, right? 3 over 2n is half a width. So that means 6 minus half a width. That would be my last midpoint. Well, that means 6 has to be the right edge. 6 has to be the right edge, so you get that. But probably better to just say, hey, the width is 3 over n times n rectangles. Total width of 3 starts at 3, ends at 6. Okay? Or if you want to do the black, just think of this as your x. So that's 3 over 2n, 6 over 2n, so forth, 9 over 2n, whatever. But that's going to be starting at 0, and then the first thing you plug in is 3 over 2n. That's half a width, right? 3 over n, which is 6 over 2n, same thing. Okay, that's half a width, so it starts at 0, total width of 3. So you can do that. So either one of those would be okay. Okay? But what are we looking for? We're basically saying, if we're sticking with the red, we're just saying, okay, all that messy stuff inside is my x. The width goes to dx. All I gotta do is plug a 1 in for k, kind of help me figure out where I'm starting, and then see what my total width is to see where I am. And that's really all you do. So going this direction, we pretty much have a set of rules. It's almost like derivative. You have a set of rules, and antiderivative is you gotta be a little more creative and think about where it came from. It's kind of the same way with these. You got the integral, and okay, I'm gonna do my x-axis, I'm gonna figure out my width, I'm gonna write out my pattern, I'm gonna see my pattern, I'm gonna write it out. Right? That's how you go from an integral to a sigma. When you're going the other way, you're just kind of having to think in reverse. And you're having to think, okay, where must the x have been? What must my starting point have been? That kind of thing. All right? Okay. So here's some problems related to that. So you can practice that a little bit, I think, in the video tomorrow. So if you're having some questions about that, or you get into it here in the next 10, 15 minutes on some of these, and then you want to get some help, right? You might go to 39 through 42 or 45 through 46. Now, here's the unfortunate thing on this homework. They give you the answer, and I hate that they did this. So on 27 through 33, they give you a sigma, but then they show you the integral, and they say, explain why this is that. So I wish, so what I want you to do is cover up with your hand, or take something, take sticky notes and cover it up. You know what I mean? So it would be much better if you would put your thumb over the right side of what the integral is and write down the sigma and then try to come up with it. Now, one thing they do, though, is they do kind of show you this thing I'm talking about. So, like, one time they might say, well, show that this sigma equals this, but then they also might say, show that this is equal to that, right? So they kind of get both of them in there a little bit, but I just don't think you can really show it. There's not much to show. You pretty much just kind of write it down. So, again, if it were me and I was trying to practice these, I would cover up the right-hand side and write down the sigma and try to come up with the n. Okay? Because that's how I'm going to give them to you. I'm not going to give them to you like they did. Now, when you get into some of the later problems, then they don't do that. Okay?